Welcome to this first episode of the podcast, The Pump Zone, presented by Pump Systems Academy, powered by Dynapro pumps. Did you know that some of the most powerful industrial machines in the world actually relied on a deliberate, constant water leak just to keep from destroying themselves?
Yeah, it sounds completely backward, doesn't it?
Right. Well, today, our mission is a deep dive into the brilliant and honestly kind of contradictory engineering of centrifugal pumps. So whether you are a seasoned engineer or just, a curious learner, this breakdown is going to give you those aha moments of how fluids actually move through our world.
And we're really looking at a journey of intense energy transformation here, going from electrical to mechanical and finally to hydraulic energy. And the star of this whole process is, well, the impeller.
Exactly. I always think of the impeller like a spinning carnival ride, but instead of people just sliding against the wall, the vanes of the impeller are actively scooping the fluid up and violently hurling it outward using kinetic energy.
That is a great analogy. And the specific design of that impeller dictates absolutely everything about the pump's performance. So that outward throw, it relies entirely on the geometry of those vanes.
So does that mean bigger pumps just have, massive vanes?
Pretty much. In large pumps, you'll typically see 5 or 6 vanes to maximize that kinetic energy transfer. But if you shrink the pump down to a smaller diameter, you actually have to drop the vane count.
Oh, wait. Why is that? Just because of the space?
Yeah, exactly. Tighter spaces mean you need to mitigate friction losses, and you really have to prevent debris from clogging up the pump.
That makes sense. I mean, I imagine tossing a heavy viscous sludge, like, say, paper pulp. That requires a completely different geometry than just moving clean water.
Oh, absolutely. It changes the entire approach. So closed impellers are highly efficient, right?
Yeah.
And they hold up incredibly well to long-term wear when you are moving clean water.
But for the thick stuff, the sludge.
For thick or fibrous materials, you have to move to semi-open impellers. They feature much wider internal passages. You are deliberately sacrificing a bit of efficiency just to guarantee those viscous fluids move without choking the whole system.
Right. So the impeller has whipped this fluid up to a massive speed. But speed isn't actually what pushes fluid through miles of piping, right? Pressure is.
Exactly.
And to get that pressure, we essentially have to slam the brakes on the fluid, which is exactly what the casing is designed to do. Where does the fluid go? It hits the casing.
Yeah, the casing physically catches that high-speed flow and intentionally slows it down.
Wow.
So by reducing the fluid's velocity, it forces a conversion of that wild kinetic energy from the impeller into controlled hydraulic pressure.
And that resulting pressure is what actually pushes the fluid through the discharge line. But if the goal is just to catch the fluid and slow it down, making one universal casing seems like the logical path.
Right.
So why bother with so many different external designs?
Well, it all comes down to application trade-offs. Solid metal casings are the standard simply because they're cheaper to cast and manufacture.
Sure, that's just basic economics.
Right. However, split casings, which literally open up into sections, are absolutely critical for large pumps that utilize internal elastomer or rubber linings.
Oh, so you can actually get inside them easier.
Exactly. Opening the casing makes it infinitely easier to access the internals for heavy maintenance and part replacement. And, all of this heavy pressurized casing surrounds another crucial component, which is the bearing housing.
Right, the bearing housing, which is doing the heavy lifting of keeping the spinning shaft perfectly aligned. Plus, it transmits the motor's power and provides the vital lubrication needed to keep the whole high-speed assembly from burning up.
Which is no small task.
Definitely not. But that creates a massive problem. We have this immense hydraulic pressure building up inside the casing. So how do we stop the fluid from just spraying out the back where that rotating shaft enters?
Well, you need a sealing system.
And here's where it gets really interesting. The most conventional, economical solution is called gland packing. And the wild part, it's the exact seal I mentioned earlier.
The one that requires a leak.
Yes, it actually requires a minimal, constant leak to work properly.
It's crazy, but true.
Yeah.
You pack these fibrous cords into the back plate to physically block the fluid. But if you compress that packing too tightly, the sheer friction of the spinning shaft will just destroy the material.
So it desperately needs a constant, tiny drip of water to provide cooling and lubrication. The seal is technically designed to fail slightly.
Right. But if an application demands absolutely zero leaks, like say with dangerous chemicals, we need a completely different mechanism.
Which brings us to the dynamic seal.
Yeah, and it's brilliantly simple. It uses a second, smaller impeller position behind the main one, but with reversed vanes.
Wait, reverse, so it pushes the fluid backward.
Exactly. It physically pushes the fluid back away from the shaft, ensuring a perfectly dry seal while it's running. The catch, though, is that it requires a minimum operating speed to create enough of that backward force.
And if you can't guarantee that high speed, you have to use a mechanical seal.
Right. A mechanical seal guarantees zero leaks by pressing two incredibly flat, highly polished faces together. One is spinning with the shaft, and one is stationary on the casing.
And because the gap between them is virtually microscopic, no fluid escapes.
Exactly. But this raises an important question, which is, at what cost? Because that gap is so precise, mechanical seals are incredibly delicate.
Like, how delicate are we talking?
I mean, the absolute slightest shaft vibration or deflection will shatter that perfect alignment and just destroy the seal. Your bearing alignment literally has to be flawless.
That is wild. So what does this all mean for you listening? I want you to think about this paradox. A centrifugal pump relies on immense, violent mechanical force to throw heavy fluids around.
Brute force.
Exactly. Yet, to keep from tearing itself apart, it requires microscopic, delicate precision in its mechanical seals and bearings.
It's a huge contrast.
It really makes you wonder, how will future engineering and advanced materials solve this inherent contradiction between brute force and absolute perfection?
It is definitely a fascinating challenge for the next generation of engineers to tackle.
Absolutely. We invite you to tune in to the next episode of the podcast, The Pump Zone, presented by Pump Systems Academy, powered by Dynapro Pumps.